So let's try some problems. So we want to calculate the cell potential for a reaction at 25 degrees C where we have aluminum nitrate and an acid making aluminum ions, so aluminum 3 plus, NO gas, and 2 waters. So the first thing that we have to do if we're going to calculate the cell potential, we have to divide everything up into the oxidation and reduction half reactions. So when I look at this, I see that aluminum's changing oxidation states. It goes from 0 to 3 plus. So that's our oxidation half reaction. And as aluminum goes from aluminum to aluminum 3 plus, it's going to release 3 electrons. So that means the reduction half reaction is the nitrate and the 4 protons going to NO and 2 waters. So it's taking up those 3 electrons. So my next step is to look at the oxidation and reduction potential values. And when I look at my table, the reduction potential for aluminum 3 plus, so that's aluminum 3 plus going to aluminum solid. So it's got to pick up 3 electrons. That value is minus 1.66 volts. But I need the oxidation potential. So the oxidation potential has the opposite sign of the reduction potential. So that's why I get the oxidation potential as positive 1.66 volts. Now I need to find the reduction potential for the reduction half. And from the table I find that that is positive 0.96 volts. Now if I want to get the E cell, remember that's the sum of the E ox and the E reduced. So we add those two values together and we get a total cell potential of 2.62 volts. So that's our final answer. Now we want to do a similar type of reaction, but we want to predict if the following reaction is spontaneous under standard conditions. And if we get a positive value for our cell potential, then the reaction is going to be spontaneous. If it's negative, it's not spontaneous. Okay, so first we want to separate the reaction into the oxidation and reduction half reactions. So the iron is going from 0 to 2 plus, it's getting oxidized, and the magnesium is getting reduced as it goes from 2 plus to 0. So there I've written the oxidation half reaction and the reduction half reaction. And so I've written both as the reduction half reactions here, so the magnesium being reduced and the iron being reduced. Because the magnesium reduction is below iron, the reaction is not spontaneous as it's written. But another way that we can do this, so if I'm looking at the chart of reduction potentials, so the reduction potential of magnesium is negative 2.37, and that for the iron is minus 0.45 volts. So the iron reaction, this one is a bigger number, so it's closer to being positive. So the iron 2 plus will be reduced. So it's bigger, meaning it's closer to a positive value and a larger positive value. So the iron 2 plus will be reduced. So if the iron is going to be reduced, that means the magnesium wants to be oxidized. But that's not the way that they wrote the reaction. So the oxidation reaction for the iron going to the iron 2 plus, so remember that's the opposite sign of this here. So the oxidation potential is 0.45. And the magnesium potential, the reduction potential for it is minus 2.37. So when I add those two up and I get the E cell, I get a value of negative 1.92 volts. And because this has a negative sign, that means it's not spontaneous. So we can predict whether a metal will dissolve in an acid. So an acid will dissolve in metals if the reduction of the metal ion is easier than the reduction of the H+. And metals whose ion reduction reaction lies below the proton reduction on the table will dissolve in an acid. So remember we said that the zinc reduction potential was minus 0.76 volts, and the proton reduction potential was defined as 0. Since this is the larger value, the protons will be reduced. So if the protons are being reduced, then the zinc has to be oxidized. So the zinc, as it's oxidized, goes from zinc metal to zinc 2+. So that's what we see here, the zinc being oxidized from zinc metal to zinc 2+. So it's going to give up its 2 electrons, give them to the protons to make hydrogen gas. And when it does that, it will start to dissolve the metal. So now we want to relate the cell potential to the Gibbs free energy and the equilibrium constant. Now if you'll remember, for a spontaneous reaction, so one that proceeds in the forward direction with the chemicals in their standard states, the equilibrium constant is greater than 1. And if it's spontaneous, the delta G value is negative, so it's less than 1. And for the cell potential, if it's greater than 0, so if it's positive, it's going to be a spontaneous reaction. So this little triangle here helps us to relate the cell potential, the delta G, and the equilibrium constant. And these equations here allow us to interconvert between the different values. So the delta G naught of a system is equal to negative N F times the E cell, and N is the number of electrons transferred, and F is Faraday's constant. And then here we're relating the E cell to the equilibrium constant. And here again we're relating delta G to the equilibrium constant, so you can remember this from your thermodynamics chapter. So again, as I previously said, N is the number of electrons being transferred here in this equation, and F is Faraday's constant, and that value is 96,485 coulombs per mole of electrons. Now in this form of the equation here, the R, the T, and the Faraday's constant, so these are all constants. They're all combined for you, and they give you, this is where they get the 0.0592, because they combine the gas constant, the temperature at 25 degrees C, and Faraday's constant all together to just give you one constant value. Okay, so using those equations, we want to calculate the delta G for the reaction of iodine and bromide combining together to make bromine liquid and iodide ions. So we look at our chemical equation, and we want to find the delta G, because that's what we're looking for. And I know that I can determine the oxidation potential and reduction potential for the half cells and use those together to get the cell potential for the combination of those. And from the E cell, I can convert that to the delta G. So remember, to get the E cell, I combine the oxidation half reaction plus the reduction half reaction to get the E cell value. And then I can use that cell potential times Faraday's constant times the number of electrons transferred times the negative to get the delta G values. So let's start solving that problem. So the oxidation half reaction is the bromides going to bromine liquid, so going from a minus to a 0. And the oxidation, I look at this reduction potential as 1.09 from the table, and I need the oxidation, so it's minus 1.09. And then the reduction is the iodine going to iodide, and that reduction potential from the table is positive 0.54 volts. So I add these two together to get the total reaction, and that gives me E cell value of negative 0.55 volts. So now that I've got my E cell value, I can plug that value in here along with my constants, and I know that 2 electrons are being transferred, so negative 2 gets inserted in for the N value, and I can calculate my delta G. So negative and the 2 moles of electrons that are transferred, Faraday's constant, and the E cell potential, which we calculated, and I should get a delta G value of 1.1 times 10 to the 5th joules. So my moles of electrons cancel out, my coulombs cancel out, and my negative charges cancel out to get a positive value. And then since the delta G is positive, the reaction is not spontaneous in the forward direction under standard conditions. And we would predict that based upon the cell potential being negative. Okay, so we've found delta G. Now let's calculate the equilibrium constant using the reaction where copper combines with an acid to make hydrogen gas and copper 2+ ions. Okay, so we're looking for the equilibrium constant. So again, we want to take the oxidation half reaction, the reduction half reaction, add those together to get the cell potential, and use the cell potential to find the equilibrium constant. And we can relate the cell potential to the equilibrium constant using this equation here. So I determined that the oxidation potential, so the reduction potential of copper 2+ is positive 0.34. So the oxidation potential of copper 0 is minus 0.34. And remember, this value comes from the table. And then the reduction potential, this is the proton becoming hydrogen gas. That's the defined value of 0. So the total cell potential is minus 0.34 volts. So now we've got the cell potential for the reaction. We can plug this into our equation here. 2 electrons are being transferred, so we can plug in the N value of 2 and just solve for K. So as I solve for my log K, I get a negative 11.5. And so to get rid of the log, so I take 10 raised to the negative 11.5, and I get a K value of 3.2 times 10 to the minus 12. So my volts cancel out. And then because the equilibrium constant is less than 1, the position of the equilibrium lies far to the left under standard conditions. Now we also want to look at non-standard conditions with the Nernst equation. So the Nernst equation allows us to look at non-standard conditions. So something other than 1 molar concentrations. A delta G equals a delta G naught, because the delta G naught, remember, that's at standard conditions, plus RT ln of Q. And Q is the reaction quotient. So this is a factor to adjust the Gibbs free energy at standard conditions for the conditions that you're at here. And that for the cell potential at non-standard conditions equals the E naught minus 0.0592 divided by N times the log Q at 25 degrees Celsius. And of course, when the quotient, the Q value equals K, then we're at equilibrium. And then nothing's going to happen if you're at equilibrium, so the cell potential is going to be 0. So we use the Nernst equation to calculate E when concentrations are not 1 molar. Now going back to the zinc and copper solution, here we have under standard conditions the 1 molar zinc 2+ and 1 molar copper 2+. And under standard conditions, if we added up the oxidation half reaction plus the reduction half reaction, we'd get a total of 1.1 volts. But in the second conditions, where we're not at standard conditions because we have less than 1 molar and more than 1 molar of the copper 2+ solution, we have a deviation from that value at standard conditions. So let's look at solving a problem. So this is our reaction. We're looking at copper and the permanganate and an acid reacting together. So the copper is going to be reduced as it goes, it's going to get oxidized as it goes from copper 0 to copper 2+. And then we have the manganese being reduced. And part of the problem, it's not shown up here on the top of the problem, but other bits of information that were given besides the balanced chemical equation is the concentration of the copper, which is 0.01 molar, and that for the permanganate is 2 molar. And the hydrogen concentration, or the proton concentration rather, is 1 molar. So they want us to calculate the E cell for that reaction under those conditions. So we first have to find the cell values under standard conditions using the oxidation half reaction and the reduction half reaction values. And then we use the Nernst equation to relate that to the E cell at the non-standard conditions. Okay, so the copper is being oxidized, and the oxidation potential for copper is 0.34 volts. Because the reduction potential of copper 2 plus is positive 0.34 volts, the oxidation is minus 0.34 volts. And the reduction potential of this reaction here is 1.68 volts, and this is from the table. Now we're going to have to multiply this reaction by 2 to get 6 electrons being transferred, and we have to multiply this one by 3 to get 6 electrons being transferred, so that my electrons cancel out on both sides. Now even though we multiplied this by 2, we multiplied this by we multiplied this one by 3, and we multiplied this one by 2, we don't change the cell values because the difference in energy doesn't change. So don't make that mistake. So when we add those two together, this is our equation. So 3 coppers plus 2 permanganates plus 8 protons to make 2 MnO2s plus a copper 2 plus ion plus 4 waters. And so the E cell for that is negative 0.34 plus a 1.68, which gives us an E cell value of 1.34 volts. So we're halfway there. We found the E cell for this reaction. Now that we have the E cell reaction, we use the number of electrons that are being transferred. So we said 6 electrons are transferred, and we have to use the log Q. And remember, this is products over reactants. So our products are the MnO2, but that's in solid state, so it doesn't show up. The water is pure, it doesn't show up in our Q value. And we had the copper 2 plus, so that goes in our numerator. So products over reactants. The copper doesn't show up because it's solid. And we have to have the concentration of the MnO4 and the protons. So there's our Nernst equation. And writing the Q, so our products over reactants, don't forget to make those coefficients. Remember, those coefficients have to become the exponents when we're using the Q values, because those are just like our equilibrium constants. Then we plug in the copper 2 plus concentration, the concentration of the permanganate, and the concentration of the protons. And remember, we said 6 electrons were being transferred. And when we do the math here, when we put this in our calculator, we should get an E cell value of 1.41 volts. So all the units are correct, and the cell potential is greater than the cell potential at standard conditions, and that's expected because the concentrations of the MnO4 minus is greater than 1 molar, and the copper 2 plus concentration is less than 1 molar. Now concentration cells, this is when you have difference in concentration, so it's possible to get a spontaneous reaction when the oxidation and reduction reactions are the same, as long as the electrolyte concentrations are different. And this difference in energy is due to the entropic difference in the solutions. So the more concentrated solution has lower entropy than the less concentrated. The electrons will flow from the electrode in the less concentrated solution to the electrode in the more concentrated solution. So oxidation of the electrode in the less concentrated solution will increase the ion concentration in the solution. The less concentrated solution has the anode. And then reduction of the solution ions at the electrode in the more concentrated solution reduces the ion concentration. So that means the more concentrated solution is at the cathode. So let's just look at a concentration cell. Now in this case we have copper at standard conditions, 1 molar and 1 molar. So since they're both at standard conditions and we have copper in both systems, the standard conditions, or sorry, the voltage between them is 0 volts. So you're not going to get any electrons to flow. So when the cell concentrations are the same, there is no difference in energy between the half cells, and thus no electrons flow. But if we change the concentrations, so in this one we have, in this first cell, we have a copper 2 plus concentration of 0.010 molar, and the other one has a 2 molar concentration. So this one's more concentrated ion, and this one's less concentrated. And if we measure the voltage difference in the system, it's 0.068 voltage. and we set up the voltmeter so that a positive reading is set up, because a positive value means a spontaneous reaction. So this reaction, the electrons are going to continue to flow until the concentrations of these two are the same. So as the concentrations of these two cells are trying to get to be the same, the copper lower concentration is going to go up in value, and the higher one is going to want to go down in value. So the only way the copper solution can increase its concentration is for the oxidation to occur. So the oxidation occurs with the less concentrated, so that it becomes more concentrated as the flow of electrons happens. And then if the higher concentration is going to be at the cathode, because at the cathode is where reduction happens. And the cathode, since reduction is happening, it goes from copper 2+ to 0. So the copper 2+ concentration is going to go down. So the less concentrated one is where the anode is, because the concentration has to increase. And the more concentrated one is at the cathode, because the concentration has got to go down. So when the cell concentrations are different, electrons flow from the side with the less concentrated solution, the anode, to the side with a more concentrated solution, which is the cathode. If we were to set up the shorthand notation, so again, we have the same reaction happening on both sides. One is just the oxidation. So remember, oxidation is happening on this end. So the oxidation. And the anode is where oxidation occurs, and those both start with vowels. And over here we have the cathode. And this is where reduction takes place. So you can see, if you're trying to figure out the way things flow, and if we're trying to figure out how to use the Nernst equation, so remember that E equals E naught minus 0.0592 over N log Q. Well, since the copper is changing oxidation states by 2, the N value has to be 2. So the number of electrons transferred are 2. But the Q value, remember, that's just products over reactants. So if we look at these reactions here, this is our reactant, and this is a product, and this is a reactant, and this is a product. So if we're looking at products over reactants, it's going to be the Q value is going to be the 0.010 molar over the 2 molar concentration. Because remember, the copper solid doesn't show up in the Q value because it's a pure form. So it's going to be the products over the reactants. So when you're looking at a concentration cell and it's hooked up right to give you a positive reading, the less concentrated will always be on the top and the more concentrated will always be on the bottom. Okay, so that concludes our second lecture video on electrochemistry.